Okay, so similar to how we approached this central limit theorem, we applied the central limit theorem first to proportions, the specifics of what that looks like, and then we applied it to means. We're going to do the same thing with confidence intervals. Okay, so like in this first example, there are conditions for our inference to be valid for us, like just like we had the condition previously to assume normality or assume that we can use our standard deviation formula. The same thing is going to be true here if we want our inference to be valid. So think about what it is that we want to do. We're constructing a confidence interval for this parameter P. It's the proportion of pennies in this particular collection, and we'll assume that they have lots and lots of pennies in this collection. I think somewhere in your textbook it mentions that they certainly have over 1,000 of them. And remember, we go into this collection and take a particular sample size, and we'll get a sample proportion. Okay, so in this situation, what did they do to get this sample? They had 57 pennies that were more than 10 years old, and that's what we're looking for, the proportion of pennies that are more than 10 years old. Okay, out of how many pennies? Well, 57, they were 45 that were at most 10 years old. So 45 that were less than 10 years old and 57 that were more. So we add those two together to get their sample size. So 57 and 45 would mean that they had 102 pennies. So I'll get a decimal approximation of that, and we get 0.5588. So what you're going to find with, especially for confidence intervals, it's actually these counts that we get for proportions that'll be more helpful to us when we check our conditions. So three things. Anytime we want to make a valid inference. Number one, did we take a simple random sample? Okay. We must consider, if it doesn't say so, the 102 pennies as a simple random sample or a representative sample of all of the pennies in the collection. You'll tend to see me do that first all the time. Did we take an SRS? It says their sample, so not necessarily an SRS, but we just need to be able to assume that we're going to state that if they tell us that or not. Okay. The second one, we want to basically make sure that each penny is independent of the next. But remember, our rule of thumb for that is that assume there are more than 10 times 102 pennies in the collection. And I believe it states in your textbook that there are. Right? Remember, the rule of thumb here is that we don't want to sample more than 1/10 of the population. So our sample size was 102. That can't be more than 1/10 of the entire population that we're sampling from. And then finally, do we have a normal sampling distribution? See how I drew these p-hats up here and I drew them in a normal shape? Do we have a normal sampling distribution? And if you remember the rule of thumb for that, it was for proportions, it was n times p and n times 1 minus p. But what do we have now? We have p hat. So think about this for a second. That's why I said the counts are going to be important to us. If I were to do n times p hat, what am I doing? 102 is the sample size times 57 over 102. So it's really just a count. So 57 is greater than or equal to 10, and 45 is greater than or equal to 10. So if they frame it to you in the context of a decimal, if they say our sample proportion was 63 and we knew it was out of 200, then we would have to figure out what that count is. Well, a lot of times explicitly they're going to give us the count, okay? So it makes life easier in that regard. All right, use table A. We'll take a look at table A to think about this critical value Z star for 96% confidence. But I want to draw a picture for you of what I'm looking for and help you realize that we can also lean on our calculator for this. So what we're saying is, what is a Z score that would contain 96% of all values in a normal distribution? Now, we should know off the top of our head this should be around 2, a little bit more than 2, because we know as a rule of thumb, 2 standard deviations in either direction is 95%, rule of thumb. The actual precise amount is 1.96. So where do I look for this table A? And more importantly, I'm going to hopefully give you a way to do this on your calculator that might be a little bit easier for you. Where did my PDF go? Okay, so table A is on your formula sheet. If we scroll down on the formula sheet here, here's table A. And what I'm looking for is a z-score that has an area to the left. Let's go back here. If there's 96% in here, we'd either want a negative z-score that has 0.02 to the left of it, right? And what's the area to the left of this one? It would be 0.98, right? Because you'd have 2% in each tail, 2% and 96% would be 98%. These two values should give me the same result. So let me see if I can grab, if we can look at that table in the whiteboard here without losing what I already have in my whiteboard. I'm looking through this table and I want to find a value as close to 0.02 as possible. And it looks like I can find this one right here, right in the middle, 0.02. So now I'm going to work backwards and see what would be the z-score that would correspond to that. It would be negative 2.05. Likewise, if I go look for that 98% number, if we try to get as close to 0.98 as possible, it looks like we would see 0.9798, right? Or 0.9803. It's really close as well, but 0.9798 is closer to 98% than 0.9803, just barely. And what's the z-score that corresponds to that? 2.0, and then the second decimal place would be 0.05. So what we're suggesting is that this would be 2.05, and this would be negative 2.05. So on our calculator, if you remember, this is an inverse norm situation. If we say to the calculator, we go second variables key and number 3 for inverse norm, and we say, look, we want the area to the left to be 0.02, and the older calculators all only do area to the left. There it is, negative 2.05. Now, if we change that to 0.98, we get the same thing. But we just get the positive incarnation of it, 2.05. Okay, so you can use table A. You can go look it up on table A to 2 decimal places, or you can use inverse norm. 0.02, mean of 0, standard deviation of 1, remember, because these are z-scores. Or we could go inverse norm, 0.98, 0, and 1. Okay, because the critical value z star is plus or minus 2.05. That's how we construct a confidence interval. We would want to add 2.05 standard deviations to the right and subtract 2.05 standard deviations to the left, and that would give us 90% confidence that that interval contains that true proportion of values that describes what proportion of pennies are more than 10 years old in their collection. Okay, so the first question here says, calculate and interpret the 99% confidence interval for P, the true proportion of pennies in the collection that's more than 10 years old. So I want to show you a tool that I've posted in Schoology for us, AP Stats, under Materials, particularly in Chapter 8, and you'll see this confidence interval template, okay? Anytime you're going to construct and interpret a confidence interval, I'm going to recommend you can go ahead and use that confidence interval template. I'll show you how it works. All right, so state the parameter of interest. So here's my confidence interval template. This is going to be P. This is the true proportion of pennies in the collection that are more than 10 years old. Okay, it's the very first thing that we want to do. Okay, the formula for the standard deviation of the sampling distribution, what's that? It's right here on our formula sheet in our inference section. We are looking at sample proportions. This is our standard error right here, p hat times 1 minus p hat over n. We'll take the square root of that. So see if I can squeeze that in here. P hat times 1 minus p hat over n, and it's not a new formula. We used this in the last chapter with central limit theorem. Okay, so again, these conditions we already verified here. Conditions for valid inference. Where did we do that? Back up here. Okay, so really, I'm just going to reiterate all of this in that place. Okay, check the conditions. So what I would write there in my template would be those conditions from our first example. Okay, so we can reference that. I won't write them all out, but we have SRS, we have large normality, large counts. But you have to verify them, right? You're gonna, you would use the numbers that we had previously, 55 and 47, or 57 and 45, right? Both greater than or equal to 10. Try not to be too redundant here, right? And then also we want to sample less than 1/10 of the population. So that the 1/10 of the population guarantees us that this formula will work for us. Okay. So how does the calculation or computation work? Let's double back and see. We want a 99% confidence interval. Okay. So I'm going to need a Z star for 99% confidence. All right. How do I get that? Let's think about it. If I have 99% in the interval, what am I inverse norming, right? I have 1% divided by 2 would be 0.005. So I would want to inverse norm right, with a mean of 0 and a standard deviation of 1, just so you can see where I'm getting that number from. So I'm going to cheat ahead a little bit. I wish the College Board would just point these out to you. But when we get to means, we're going to use, instead of the Z distribution, we use this adjusted T distribution. If you sneak down to the bottom here and take a look with me, see these percentages here, confidence levels, 50, 60, and these degrees freedom for infinite. This should just say Z star. These are your Z distribution. Notice we just did 96%, and here it is, 2.054. All right. So 99%, we should get 2.576. Well, let's see. What happens when I inverse norm 0.005? Or 0.995, right? We could do either one of those. There it is, negative 2.576. This is right here, 2.576. So if I had inverse normed the positive incarnation of that, that's what I was suggesting there, which would be 0.995, right? I have the 99 in the interval, and then another 5 in the tail. This would go 99, and there's our 2.576 as well, okay? So you get negative 2.576 or 2.576, right? So why am I bringing that up? That's how I'm going to compute my interval. I'm going to take my point estimate, which if we go back here and see, was 0.5588, right? It's p hat. It goes like this. I'll write the formula out so you can see. It's going to be p hat plus or minus a critical Z value that's based on the confidence level times our standard error. We want to add and subtract a certain number of standard errors from that. So this would be 0.5588 plus or minus 2.576, okay, times that standard error recipe. So what do we get when we do our standard error? So let me just double check my data here, 0.5588, right? So that's my p hat. So I take 0.5588 times 1 minus 0.5588, and then we divide by the sample size, and we take the square root of all of that. So I get 0.049. Okay, and then we would multiply that out. So we take 0.5588 plus or minus 0.1266, and then I express that as an interval. So my interpretation in context, we don't want to get too carried away with having to explain what confidence means. We just say we are 99% confident that P, and we already defined what P was, is contained in this interval. Right? So this is why I like the template. Your textbook authors use the state, plan, do, conclude, but I already wrote up here what P was. It's right there. So I don't have to write it again. We're 99% confident that P is contained in this interval. Now, if we ask a question like, what do we mean by confidence? then we have to be a little bit careful how we articulate that. So let me go to the calculator and show you how the calculator will take away all the heavy lifting for us, or at least so we can check our work. Okay, on the calculator, and this is where we are going to live for most of the rest of the year. We are going to be in the stat and test situation. For folks that use the NSPIRE, you're going to go to statistics, and then you should see test. There's going to be 2 places for you. You're going to have confidence intervals and tests. So you would actually want to look up under confidence intervals. For us with the older calculators, everything is under tests. So if you're having trouble finding this on a NSPIRE, just check in with me and I'll walk you through where it is. It actually kind of has its own place. It has the intervals for you. So we want to be careful what we pick here, otherwise things will go sideways and you'll be looking for the wrong things. We don't ever, even though this seems like this was a Z interval, this is a Z interval for means, which we never ever do. So if we could delete that or erase it out of the menu, I would. What I have here is a 1 proportion Z interval, and I don't see that on my screen. I have to go down or up a little bit. But what I have here is 1 proportion. You'll see sometimes we want to compare 2 proportions. Maybe you have proportion of pennies in this collection and compare it to the proportion of pennies in some other collection. But this is just 1 collection, 1 population, 1 sample. So it's a 1 proportion Z interval. That's what we want to look for here. All right. And in fact, in this chapter, in chapter 8, there's only 2 things. You're either going to select a 1 proportion Z interval or you're selecting a T interval. Nothing else. So if you want to write those 2 things down for chapter 8, that is it. That's all we are doing. So what did we have here? Again, let me just double back to make sure. We had 57 out of 102, right? So there were 57 pennies that were more than 10 years old out of a sample size of 102. And we wanted 99% confidence. So I just put in 0.99. And the calculator will do all of the heavy lifting for us. So we'll compare our answer and see if the result we got was pretty close to that 0.432, 0.685. Yeah, 0.432, 0.685. So negligible difference there in like 3rd, 4th decimal place situation. And then this is our interpretation in context, okay? So now let's get back to the second part of this question. All right, I hashed out my confidence interval on the template. Is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? So we go back and look at our interval, and we can see that 60% is inside of our confidence interval, so we would say that it is plausible. This is where we can start to make these statistical inference answers to things. If somebody were to say they think 70% of the collection is more than 10 years old, I would say I'm 99% confident that's not true, right? Since 70% is not in this interval, I can be 99% confident that P is not 70 or that it's less than 70. But in this case, 60% lives in the interval, so it's a plausible value. Okay, so since the value of 60 lives in our confidence interval, right, that goes from 43% to 68.5%, it would be a plausible value for P. I wouldn't argue with somebody that believed that was true. It doesn't really prove that it is, but it's a plausible value. Okay. All right, one last confidence interval here, and this one is pretty much worked out for us. We'll just do a little bit of algebra in the end here. But in her first grade social studies class, Jordan learned that 70% of the Earth's surface was covered in water, so she wants to see if this is true. They toss around this globe, being careful to spin it. When she catches it, she records where her index finger is pointing. In 50 tosses, there were 33 out of 50 that were landing on water. So that's, we can, hopefully do in our head 66%. And we're going to construct a 95% confidence interval to check this claim. So your textbook authors, instead of using my template that I've set up, they have a state, which is where they state the parameter of interest, which is part of my template. Plan, which is where we check our conditions for inference. Do, this is where we calculate the interval, and this is where I say, express your conclusion and confidence. This basically is my template, but they use the state, plan, do, conclude as their instructions. And then they come up with this interval, and you can see 70% lives in that interval. So it's a plausible value. It doesn't prove it by any means, but her confidence interval, her little experiment, her investigation here doesn't give any reason to doubt that claim. Okay. All right, so now this is a little bit different question. How many students do we need to survey so that our margin of error is 10%. Okay, so with 95% confidence, remember what that means. Z star is going to be 1.96. You're going to use that so much that you'll probably end up having it memorized, but if you don't, you can jump to your formula sheet and see 95% confidence. Remember, you have to go to the t distribution for this. Don't look for this in that z distribution. And t will be familiar to you by the end of this chapter because we will use it for means. So here's 95% and 1.96. If you didn't know to do that, we can just go second vars and do our inverse norm. We're not going to inverse norm 0.95. We're going to inverse norm 0.95 plus a tail, which would be 0.975, right? Remember, if I want 95% confidence, that's what lives in the interval. So that means that you've got 2.5% in each tail. So either inverse norm 0.025 or inverse norm 0.975. And I get 1.96, right? Which is right there on the chart. Okay, and you get the same thing if you inverse norm 0.025. Okay, so we have a z star of 1.96. So remember, how do we get our margin of error? This is what your confidence interval formula looks like. Plus or minus z star times p hat times 1 minus p hat over n. For a confidence interval, this is what we call our margin of error. Right? It's really the width of the interval. This value here, p hat times 1 minus p hat over n, this is what we call our standard error. It's the standard deviation of the sampling distribution from central limit theorem. So this is really just an algebra exercise, okay? Suppose that you want to estimate P, the true proportion of students at your school that have a tattoo with 95% confidence. So since I don't have any preliminary estimate for P hat, what should I use? If I don't know anything about P hat, we just use 0.5, okay? If P hat's completely unknown, use 0.5, and that'll give you, the highest possible sample size that you would need. Okay, so we want this margin of error to be no more than 10%. So I take 0.1 and I'm going to set it equal to 1.96 times the square root of 0.5 times 0.5 over n, and we're solving this for n. So it's a little bit of algebra gymnastics. How would I solve this for n? Well, the first thing I would do is divide both sides by 1.96. And I'm going to leave this alone till the end. And now that's equal to 0.25 over n, all living under the radical, right? So how do I get to that n? Two more steps. Square both sides, right? So we have 0.1 over 1.96 equals 0.25 over n, but I'm going to square both sides, okay? And then finally, the trick to solve for n, if you have a proportion like this, you can just switch these two. I'll show you what I mean. If 20 is equal to 40 divided by 2, then it ought to be true if I switch these two. That 2 ought to be equal to 40 divided by 20, and it is. So that's all I'm going to do. I'm going to say that n has got to be equal to 0.25 divided by 0.1 over 1.96 squared. Just a little bit of algebra there. And I get 96.04. Well, guess what? We're going to have to round that up, okay? We would need 97 because I can't let if I make this answer for n be 96 instead of 96.04, we know we can't have 96.04, then it's going to compromise that value of 0.1. 0.1 is going to have to be a little bit bigger than what we want it to be. And we're okay with the margin of error being a little bit smaller, but we don't want it to be bigger, right? We don't want to compromise or make that sacrifice, okay? So just an exercise in algebra there in that situation to find sample size.